So good afternoon, everyone. Just a quick announcement. For the social dinner, the bus will leave at 7 sharp from the hotel. So please be there at 6:55. Okay? Okay? Okay. And the bus, yes, goes back right after the session. So today, of course, today. 3:30. For tonight, 6:55. There at the lobby. Okay, so it's a pleasure to introduce the chairman, Sandy Feder. Thanks, Sandy.
So we're very happy to have 3 talks this afternoon. And the first talk will be Anna Minguzzi.
So thank you very much. So I would like to start by thanking the organizers, Tommaso, Christophe, Leonardo and Luis, for the very kind invitation, and it's great to be back in Natal. And so the topic of my talk is, generally speaking, the study of the non-equilibrium quantum dynamics of an interacting system. But in particular, it is in the framework of the Josephson effect. So the Josephson effect in its simple form is a macroscopic quantum coherent phenomenon where you have two quantum systems weakly coupled by a tunnel junction, and they can be simply described in the basic form by just 2 complex amplitudes related to the density and the phase, or the particle number and the phase of each of these 2 quantum systems. And then by studying the dynamics of relative numbers and relative phase, you end up to simple equations introduced by Josephson. For the first one is the variation of the population in terms of the sinus of the phase difference. And the second one is the equation for the phase in terms of the energies of the 2 quantum systems. So this is, of course, very well known and very exploited already for many applications in superconductivity. But it exists also in our field, and in particular with ultra-cold atoms. And it can be realized in at least 2 ways. The first one is called the external Josephson effect. It is obtained by a double well potential separated by a barrier, and you have 2 matter waves which are weakly coupled across this barrier potential. And the second way is called the internal Josephson effect, and then can be done by using 2 internal hyperfan states of an atom and sharing the same external potential. So the very basic model, the simplest model we can think to describe this system, is done within the mean field Gross-Pitayevsky equation, on top of which you can make a 2-mode approximation. That is, that you assume that you attach to each of the condensate a spatial orbital that does not change in time, times a time-dependent complex amplitude. So this model was then a generalization of the model for superconductors, because in our systems we have a strong effect of interaction, adding a nonlinear term in these equations. And of course, you can get all the microscopic parameters of this model by the knowledge of the trapping potential and the mass of the system. And this model was introduced by Augusto Smerzi, who is here in the audience. And the model was actually very successful to explain the first experiments, and actually it was coming before the experiments, so let me be more precise. It predicts, in particular, the possibility of having Josephson oscillations among the 2 wells of the condensate. And you can also have a second effect called the self-trapping if the interaction parameter is sufficiently large. So, of course, the next step is to study what happens in the quantum regime, where the mean field approximation does not apply. And some time ago, we studied the quantum version of this 2-mode model that amounts to studying a 2-site Bose-Hubbard model. And in this case, you have, for example, number squeezing, or also the possibility to create dynamically some non-classical states like macroscopic superposition of phase states. And more generally, one may ask what happens beyond this 2-mode model. And for example, if you do a full calculation in a spherical, by assuming a spherical trap for each condensate, and that leads to damping of the Josephson oscillations and to some loss of the coherence. So what I am interested in our work is to go beyond, let's say, the zero-dimensional version of the Josephson effect and to study more a one-dimensional-like geometry. So in this case, you can think of two possible ways of realizing the Josephson effect. The first one is by choosing parallel tubes, and this is done typically in the experiments in Vienna, in Jörg Schmidt-Meyer group, where they have obtained very results in the last years. I can list, for example, studies of the long-time dynamics and prethermalization, the possibility of realizing the Sine-Gordon model and the possibility to access to higher order correlation functions. And also there you have observed the damping of the Josephson oscillations, which to date, to my knowledge, is not yet explained. A second geometry that you can think still remaining in a 1D configuration is the one used in the Florence experiment, the group of Giacomo and Roati and Matteo Zaccanti that are here, where they have basically taken a single tube and split it in half by a localized barrier. And also in this case, you can study the Josephson effects in terms of the dynamics of population imbalance among the two parts. And in their experiment, the quantities trapped are fermions in strong interactions, and they have studied the BCS-BC crossover and the Josephson effect. And also they have understood that in their case, phase slips play an important role in the dissipative dynamics. Now, in our case, we are going to stick to a geometry similar to the Florence experiment, but going really strictly in the 1D regime, as well as using bosonic isotopes. So in particular, I will show you how because of the fact that we are in 1D, interaction effects may be very strong. And in this case, we have an important effect on the Josephson oscillations, and in particular, some damping. And let me also mention this model is equivalent to a boundary Sine-Gordon model. And we will map it onto the model of a quantum particles in a bath. So in practice, the plan of my talk is the following. First, I will describe the Josephson oscillation in these two coupled one-dimensional systems in the strongly interacting regime using the Luttinger-liquid approach. And secondly, I will test this Luttinger-liquid approach with an exact solution valid in the infinitely interacting limit. And this will allow us, by coupling together these two methods, I will provide some microscopic origin for the damping of the Josephson oscillations in this specific case. And finally, quite surprisingly, we have noted that same type of idea applied to a completely different problem, that is ultra-cold atoms interacting in a ring with a weak barrier and applied to an artificial gauge field. So in this case, I will introduce the concept of a dual Josephson model for the oscillations of the current. So let me say even more explicitly that all the talk will be focused on the one-dimensional systems, and they are very peculiar, as in this case there is no true off-diagonal long-range order, and so there is not perfect phase coherence from one part of the tube to the other one, and phase fluctuation play a major role. So the one-body density matrix that corresponds to the phase correlation function decays as a power law at zero temperature with an exponent that depends on the interaction strength. And it gets, let's say, quantum fluctuations are more and more important at increasing interaction. This constant kappa is known as the Luttinger parameter, and will come later as well, again in the talk. So also, it is interesting to mention that for one-dimensional bosons, it is possible to study experimentally all regime of interaction, and the regime of very strong interaction has been achieved experimentally. So we, as a theorist, we are allowed to tune the interaction basically from 0 to infinity in a realistic way. And in particular, experimentally, it has been studied, well, many aspects, so the density profiles, the momentum distribution, some higher order correlation functions, the frequency of collective modes, the transport of one impurity in an interacting gas, number fluctuations, and so on. So theoretically, we are going to use a model, a simple model Hamiltonian that dates back to Lieb and Lineger. It's called the Lieb-Lineger model, with bosons with delta interactions in one dimension. And this model, in absence of an external confinement, so if we drop this potential V, is an integrable model for which we have access to the exact expression for the ground state energy as a function of the interaction strength. And by the way, the interaction strength can be expressed in a dimensionless way by taking the ratio of a typical mean field energy, G times the density of the gas, divided by a typical kinetic energy constructed again with the one-dimensional density. And there are many possibilities to reach strong interactions. One is to increase G, and the other one is to decrease the density. So let me go now to the first approach that we used to study the dynamics of coupled tubes, and this is the Luttinger-liquid approach. So this is a quantum field theoretical approach that is a quantum hydrodynamics approach that is based on two quantum fields. One field phi is the field associated to the phase of the gas, and the field theta, whose gradient gives the density fluctuation of the gas. So in practice, the Hamiltonian of each of the two tubes, taken for the moment as independent, can be written as a kinetic part, like the square of the velocity of this fluid, and an interaction part that is the square of the density fluctuations. And in this Hamiltonian, two microscopic parameters have to be provided, and these are the sound velocity and the Luttinger parameters, so V and kappa. Yes, yes. So then for each of the two tubes, we introduce these fields. And then, to couple them, we introduce a tunnel Hamiltonian term that is proportional to, so that is associated to the Josephson energy times the cosine of the relative phase of at the position of the barrier. So phi plus minus phi minus at the position of the barrier. So the Luttinger-liquid Hamiltonian allows us to describe the low energy properties of this system, and this can be used every time that the excitation spectrum of the gas is linear. So in particular, it does not apply at zero interactions, but otherwise it's very well suited to treat intermediate and strong interactions. And also, let me mention that in this approach, we are treating the tunnel term as a perturbation, while the Luttinger liquids will be described by, like, as systems in the infinite barrier case. So to go slightly bit more in the technique that we use to solve this model, we have used the Luttinger liquid theory for a finite system. This is similar to the one for an infinite system, except that in this specific case, we take into account the discretization of the excitation modes in each tube. And in particular, there is the lowest mode in the system called the zero mode, which counts the number of particles. And it's associated to an operator n, which is conjugate to another operator phi, which is the zero mode phase. And these two are conjugate. And also from now on, I will just focus on the relative number and relative phase problem, and I will drop the so-called center of mass. So the other part is not important. And moreover, let me go back just a second to this tunnel Hamiltonian. So you see that in the argument of this cosine, there is the full phase field, including all type of modes, the zero mode and the non-zero mode. So the first, the important step that we have to perform is a unitary transformation which translates these phases and transfers the non-zero mode part outside of the cosinus. By doing this transformation, we get to the final Hamiltonian, which has the following form. It is the Hamiltonian for a Josephson junction, which with a quadratic term in the number of particles and the cosinus of the relative phase of the zero mode, plus a term which corresponds to a bath of harmonic oscillators that corresponds to the excited modes of each tube, and these are coupled to the number operator of the junction. So this model is known as the Caldera-Leggett model, and but at difference from the usual ways this model is introduced, the bath in this model is intrinsic of the system. So we did not have to assume the existence of an external bath. So now let's discuss. This NX is the number of excitations that you provide initially. For example, it can be an imbalance of the particles fixed by some external chemical difference of chemical potential in the two. This is the it's all so it's not the full Hamiltonian, but it includes a part of excitation modes. In particular, if we diagonalize this and go to sum and difference of these phase fields, then we are left with some quadratic part for the phase differences and the quadratic part for the phase sums. So the quadratic part with the sum is a non-interacting theory, and while the phase difference is interacting in the sense that there is this cosinus term that couples. Yes. Right. So now let's look at the specificities of this generalized Josephson junction Hamiltonian. We have introduced two parameters. One parameter is the quantum energy, and the other one is the Josephson energy. So this quantum energy corresponds to this, is associated to the mass of the harmonic oscillators, of the phonons, let's say, of this fluid, and then this mass depends on the interaction. In particular, is associated to the Luttinger parameter and the sound velocity. So both of them can be obtained from the integrability of this model using the Bethe ansatz, and this picture shows how the Luttinger parameter and the sound velocity depend on the interaction strength. And as this mass is constructed, we note that at increasing interaction, the quantum energy increases. On the other hand, if we now look at the Josephson energy, this quantity also also depends on the interaction, but it actually decreases. And this we have studied in a work with Davide Rossini and Matteo Rizzi some years ago. And it's this region of interaction strengths here where you see that the Josephson energy decreases at increasing interactions. So in practice now, to be able to describe the dynamics of this system, we have to study whether the quantum energy is larger or smaller than the Josephson energy. In the first case, when we have a very small quantum energy with respect to the Josephson energy, that means that the relative phase is well defined, and we are in the usual regime of the Josephson effect, where we have, in particular, Josephson oscillation for the number differences. But due to the presence of the bath, we have some damping of this Josephson oscillation, as well as a small frequency shift. So, and we have then an expression for this damping in terms of the microscopic parameters, and we see that by tuning either the interaction or the barrier strength, that is the Josephson tunneling, we can address two different regimes for this oscillation, from underdamped to overdamped. And in particular, in the weakly interacting regime, the Luttinger parameter kappa is very large, and this damping rate vanishes, thereby recovering the two-mode model in the mean field regime. The opposite regime is the regime where the quantum energy dominates over the Josephson energy, and in this regime, the Josephson tunneling is just a small perturbation. So this is a regime where the relative number of particles is very well defined, and the oscillations in relative number resemble much more, rather than usual Josephson oscillation, to some Rabi oscillations induced by a level splitting to do this perturbation associated to the Josephson coupling. So in this regime, our Luttinger-liquid model assumes that there is no damping because the energy scale associated to the phonon modes is too large. So the Luttinger-liquid theory predicts undamped Rabi oscillations. So now let us check all these predictions using an exact solution. In particular, there is one point that we can solve exactly, and this is the point where the Luttinger parameter kappa is equal to 1 and corresponds to infinitely strong interactions. In this regime, we have access to an exact solution for the full quantum dynamics using a mapping onto a Fermi gas, mapping to Girardot, which is actually the same thing in the lattice case of doing a Jordan-Wigner transformation from hardcore bosons to free fermions. So in this specific case, we set up the description, microscopic description of the system as described by this piecewise constant well, with the step on one of the two sides that at time 0 is set to 0, and then we follow the dynamics associated to this preparation of the state with an initial imbalance. And then by using the full quantum solution, we can obtain the number imbalance as a function of time. So this is these are the predictions for this exact solution. Let's look first at the blue dotted lines. These are the results at 0 temperature. And indeed, the calculation is done in a regime where the quantum energy is much larger than the Josephson energy. This is because at increasing interactions, we end up in this regime. And we see undamped oscillations in agreement with the Luttinger-liquid predictions. On the other hand, if we do the same calculation at finite temperature, that is this continuous line, we find that we have some damping in the oscillations. Thank you. And this damping was completely unexplained because it's not included in the Luttinger-liquid theory. So we tried to understand more this point, and to do that, actually we have, since we have the exact solution, we have access at all the excitations that take part in the quantum dynamics. And so this is a plot of the spectral function, including all the excitations that are involved in this Josephson dynamics. And the exact solution corresponds to this gray shaded area. And the dots correspond to the Luttinger-liquid solution. So we see that at small momenta and low energy, the Luttinger-liquid solution in general is quite a good approximation. But still, we found by zooming on a completely different energy scale that is associated to the Josephson energy, extra modes that are not included in the Luttinger-liquid spectrum. So this type of extra modes are those that are responsible for the damping of the Josephson oscillations. So to conclude this part, we have understood that we can map the Josephson junction in the problem of a quantum particle with a bath, and we have discussed the two regimes, one regime of the usual Josephson oscillation, valid at, say, weak and intermediate interaction, and another regime of Rabi oscillations that is more often found at strong interaction. And we have provided a microscopic explanation for this damping. And now, quite interestingly, let me explain you how all this can be applied to particles on a ring. So let us again consider the Luttinger-liquid model with its limitations, and in this case, for a ring with a weak barrier. So again, we write a Luttinger-liquid Hamiltonian. In this case, there is just one phase field and one density field because it's just one fluid. And then we add a barrier potential that is actually the so-called backscattering term in the Luttinger-liquid language, and it corresponds to the fact that if you put a barrier in an interacting fluid, it creates some wiggles, the Friedel oscillations, and these Friedel oscillations are characterized by this type of term in the Hamiltonian. And notice also that there is a minus sign difference with respect to the Josephson Hamiltonian, but this minus sign is hidden in the fact that in the Friedel oscillation I have a typical phase theta barrier, so a dephasing, that is due to the fact that when you put a barrier, you have a minimum of the density in the position of the barrier, not a maximum. So of course, we could test this by comparing with exact solution. So putting all this together, we find that a Bose gas in a ring can be described by a similar Hamiltonian as the one of the Josephson, but in this case, in place of the phase associated to the phase of the superfluid, there is the phase field theta associated to the density fluctuations. And in this case, the quantum, in this case, the conjugate variable to this to physics phase theta is the angular momentum J that corresponds to the current flowing in the ring. So essentially, we can then use the same type of analysis to predict that if you make a sudden change of the applied gauge field or a phase imprinting, this will induce oscillations of current on the ring, and this oscillation can be of Josephson type. And so we can use all the concepts and tools that have been developed for the Josephson effect to describe the current oscillations on the ring. And then it can be either in the Josephson regime or in the Rabi regime. And in this case, it's like the working point for a flux qubit. Just in this special case of the ring, we have also performed a further study. For example, what is the oscillation frequency as a function of the baryon strength in the exact Tonks-Girardot calculation? And we see that we recover both the Rabi regime and the Josephson regime at larger barrier strength. So, and with this, I would like to conclude and to remind the main results that that I have presented, in particular the study of these dynamics of imbalanced fluids in terms of either Josephson or Rabi oscillation, and we have understood what are the modes that give rise to damping. In our case, they are beyond the Luttinger-liquid theory. We would need a full Sine-Gordon theory to take them into account, or the exact solution in the infinite interaction limit, and the fact that we can view the oscillation of the current as a dual oscillations. So then I would like to thank the people which have helped me in this work, so Joan Paulo Gomez and Frank Hecking from Grenoble, Veronica Uffinger from Barcelona, and then the team of Laboratoire de Physique de Laser, Romain Dubessy, Paolo Pedri, and Hélène Perrin. So, and I thank you for your attention.
Thank you very much for that nice talk. Are there questions? Anyone?
Yes.
So where does the length